In this video, we'll look at an example of how to apply the method of undetermined coefficients, and let's just recap what the steps are. Alright, so if we have a non-homogeneous second order linear differential equation, then what we do first is we let the right hand side equal 0. So instead of considering an arbitrary forcing function on the right hand side here, we let that be 0 and solve what we call the corresponding homogeneous equation. Alright, we know how to do that well when we denote the general solution of that equation, which will involve some arbitrary constants k1 and k2, say by y sub h for homogeneous. Second step, find a particular solution to the non-homogeneous problem. Alright, so non-homogeneous is where we have the function g of t, which we call the forcing function on the right hand side. What we do there is we find one particular solution to that. And we're going to do that by guessing the form. If it's an exponential, we're going to guess an exponential up to a constant. Alright, and likewise, if it's a constant function, we'll guess a constant. If it's a linear function, we'll guess a linear function up to arbitrary determined constants a and b. If it's a cosine or a sine function, then we're going to guess a linear combination of sine and cosine up to constants a, what I'm calling capital A and b, which we're going to determine. If our first guess doesn't work, we're going to multiply it by t. That usually will. That has the effect of shifting the derivative. Okay, and a couple other things to note. If we have a linear combination, then we're going to just take a linear combination of those two. And then lastly, the general solution of the non-homogeneous problem is just results by adding your answers for step 1 and step 2. Or say, take your particular solution, add it to the general solution to the homogeneous problem, and you've got the general solution to the non-homogeneous problem. All right, a lot of this has to deal with a couple of things. One of them, one big thing being that the differential equation is linear. All right, so let's apply this in an example. So here we have our first example. We're going to solve the associated homogeneous problem, which I've got down below here. Again, we do this by our usual technique where we're going to be plugging in y equals e to the st. I'm going to go forego some of those details here, but you take two derivatives, substitute it in, and then that's going to result in solving the resulting characteristic equation. S squared plus 4s plus 3 equals 0. This is a quadratic polynomial which factors, and we would get s plus 3 times s plus 1 equals 0. Alternatively, we could solve this using the quadratic formula, and then setting each of these factors equals 0, we would get the two solutions, negative 3 and negative 1. All right, now what does that tell us? The general solution, which we're going to call y sub h of t, is going to be a linear combination of these two. So if I call S1 negative 3, then we'd have e to the negative 3 as one solution, and then the other one would be e to the negative t. So we're going to call them the general solution k1 times e to the negative 3t plus k2 times e to the negative t. All right, so that's the answer for step 1. Okay, now we have to find one particular solution to the general, to the non-homogeneous problem, which we're calling NH. Again, NH for non-homogeneous. And we're going to denote that by y sub p. Alright, so what we're going to do is look at the right-hand side function. In this case, what I've called before in previous videos is g of t. It's a constant function. That tells us we're going to guess a constant function, or in other words, a polynomial of degree 0. So we're going to just guess a constant. Alright, now what we do is we actually plug that into that differential equation. So we need to take two derivatives. So what's the derivative of a constant function? It's 0. Its second derivative is therefore also 0. So when we go to substitute it into this differential equation, what I like to do is put in y sub p double prime, right? Y sub p prime plus 3 times y sub p to substitute the y's by y sub p's, and then we're actually just going to substitute the respective formulas in. Well, what did we end up getting? We got 0 for the second derivative, 0 for the first derivative. So I'm just going to write the whole differential equation out. Right, and a good way to do this is really actually to put open parentheses for those expressions and then substitute what you get in. We got 0 for the first derivative, 0 for the second derivative. The original guess was just a constant. We're calling it a constant coefficient to be determined. Alright, now simplify and solve this resulting equation for a. In our case, the first two terms go away. There's 0, so we get 3a is equal to 2. When solving that gives us that a is equal to 2/3. Alright, so that tells us what our particular solution is. In this case, it's a pretty easy function is just a constant function, which is just 2/3. Okay, good enough. Now that's step 2. Step 3 is quite simple. We're just going to add the results together. So what's y of p going to be? Y of t, pardon me. It's going to be taking our result from step 1. The general solution we found in step 1 was k1 times e to the negative 3t times k2, or plus k2 times e to the negative t, and then we're going to tack on our particular solution. Okay, now that's not quite it for this problem. The last step really would be to enforce the initial conditions. All right, now I'm not going to do all the details here, but the initial conditions in this problem above are, y of 0 is 1 and y prime of 0 is equal 0. If you go through, take the derivative, and enforce the initial conditions like we've done in other examples, what you're going to find out is that k1 comes out to negative 1/6 and k2 comes out to 1/2. Okay, and plugging those numbers in then allow us to solve the initial condition, which would give us negative 1/6 e to the negative 3t plus 1/2 e to the negative t, and then plus 2/3. All right, and the last thing I'm going to do here is to graph this solution. Okay, and I just want to just note though, like I said in the previous video, if you're talking about a damped harmonic oscillator, which we are here, then the natural response, which is y sub h, the general solution, or the solution to the homogeneous problem in this case, if it's damped, that's going to go to 0. And we're seeing that by that exponential growth going to 0. So what is the whole function approach? The whole function approach is 2/3 as t goes to infinity. T gets larger and larger. All right, so I've got a graph of this which I created in Maple below here, and we can see that the exponentially decaying functions that we have at the beginning damp out and it levels out. In this case, it's going to level out to 2/3 because our particular solution was, in this case, keep in mind, right, that y sub p came out to a constant function. All right, so it's going to approach that constant function as t gets larger and larger.